example, if you have this formula versus this formula, okay, the LATE is compared to 2 is different. So this indicates it's the salt, the corresponding salt of this guy. So from this realization, you know that this is going to be the acid, and this is the corresponding salt, okay? So now we learn how to do buffer before. So if I gave you these two chemicals, two separate chemicals, and dissolve into water, then it's going to give you buffer, right? That is an ingredient for making a buffer. So you calculate, if I give you these concentrations, and calculate what is the pH for this buffer, then you will need the Ka value, okay? The Ka for this guy only, you look up the table, then it's going to be like that, then you just plug in the buffer equation, okay? So how to get a magic number 2, you know, is a 0.02 over the 0.01, okay, within the log here is a ratio, okay? So you end up with 2. So the buffering pH is that, okay? I thought the loading was slow, therefore I split into another one. Okay, in the previous discussion, we talked about monoprotic acid, mono meaning one, right? One proton. So here we will talk about polyprotons, polyprotic acid, so things like H2A. So H2A ionized once to give the H plus, which is acid, plus the HA minus. So that equilibrium by itself is Ka1, okay? Then the HA minus will continue to ionize, depends on Ka2. So the HA minus now ionizes into another proton to give A2 minus. So the degree of products will depend on the K values, right? Because a proton being the product, so it will be Ka. Now generally, which is true, Ka1 will be much larger than Ka2, as you can imagine, right? The logic here. So you have H2A. This will generate H plus simultaneously. You have HA minus. So this is Ka1. So now the HA minus try to give off proton. But now the protons already there will say that we are here already. We don't like as much protons to come out anymore. So there will be a suppressing effect. Okay, the protons here will push to the reverse reaction. Yet this says that we still want to give out some protons, so let's fight, you know. So the Ka2 will say that you still be able to generate some proton, you know, after the resistance, but it's still forward. So as you can see then, you know, this Ka1 will be much larger because there will be no proton to begin with in neutral water. So it's free to give off proton. Okay, once protons are there, then there will be a resistance effect. So Ka1 is much larger than Ka2. And when you solve for the proton total in this solution, then this proton total will be virtually come from the Ka1 dissociation. Okay, you still have some here, but that amount will be negligible. So this is good news. Then when you see that, then you can reduce the H2A as if it is a HA and employ Ka1 only in your calculation. So the calculation will be as usual, whatever the H2A analytical concentration is, at equilibrium, like that, okay? So an example is like this, your analytical concentration of malonic acid. Notice the formula. The formula has 2 protons. Okay, the 2 protons can come out. So K1, K2. So K1 is 10 to the minus 3, and K2 is 10 to the minus 6, right? So it's 1,000 times smaller for K2, and therefore Ka1 will dictate for the proton contribution. So you do that, okay? But be careful though. When it's down to here, 0.15 minus the x, Ka1 is 10 to the minus 3. So 10 to the minus 3 take square root is about 10 to the minus 1 something, okay? So this is going to 10 to the minus 1 something, so will be of similar magnitude to this analytical concentration, right? When they are similar magnitude, then you cannot neglect this x. This is not negligible, okay? Then you employ quadratic calculations all the way and get that answer. So review this when you review the concept, quadratic equation, and see if you get this. Jeremy?
But you just neglect Ka2?
Right. So in this calculation, we employ only Ka1. Yeah.
Is there any point in time when you have to use K2?
We will do that later. Yeah. But for now, this is the easiest case. Okay, continue with this generally speaking to be true. Okay, so if you mix 2 chemicals now, the H2A and the corresponding salt, that is, for example, sodium, hydrogen, whatever, with this kind of formula, then you realize that this is acid and this is salt. Then you can call this is acid, this is base. So once you realize that, then you're going to make a buffer, okay? Now, how do you calculate the pH for that mixture? So that is, you are solving for this guy right here, right? So now you can look at this as if it is your buffer equation already, okay? Then the HA minus will be the external amount of this guy. So you just plug in, calculate the number of moles there and plug into here. And for the acid, then you plug in here. This tool will not be, this tool will be experimentally determined. They may not be equal, okay? Then you solve for that. Okay, now, if you have 2 chemicals like that, both of them are salts, okay? This is sodium hydrogen salt, okay? Let me return some examples so people can pay better attention. Spencer. Okay, so now, physically speaking, these are two chemical bottles. This is a salt, this is a salt. However, in calculation, this is acid. This is acid. This is salt base. Okay? So this two, you can keep it.
That's not mine.
Oh, I see. Yeah. Get stuck to it. Okay? But then now, which K do you use? It's not the Ka1, but it's the Ka2. So notice the ionization. H2A, ionize, HA, A minus. So here simultaneously you get H plus. Simultaneously you get another H plus. So this is Ka1, this is Ka2. So now you have thrown in that as a chemical. You thrown that in as a chemical. So the trick is you're going to sandwich the Ka2. So the equilibrium will be between these two. So this is how you express it. So Ka2, things on the right over things on the left. So it's going to be like this, these two chemicals at equilibrium to the proton. Okay, so this is again your buffer. Okay, then for example, Ka2 is this. Then if you prepare the chemicals with this concentration, then the proton is soft to be of this concentration. So there's a buffering pH, 5.18. Okay? So on exam, I may give you practical problems, right? Practical questions. I said, okay, here is 2 grams of sodium hydrogen phosphate. And here is 3 grams of sodium dihydrogen phosphate mixed together. Then what is